Hello everyone and welcome to this lecture. Till now we have seen that eigenvalues are limited in power in the sense that they cannot determine the whole structure of graph. Okay. So there are graphs with different structures, but they can have the same eigenvalues with respect to adjacency matrix, maybe sometime with respect to Laplacian matrix, sinuous Laplacian matrix, and then we have also seen the Seidel matrix. Okay, and then in fact we have given a technique that possibly can give us the non-isomorphic graphs, but they have the same eigenvalues. We call such graphs co-spectral graphs. Okay, and that we have done with respect to adjacency matrix, the famous GM switching. Okay, in this lecture we will see that there are graphs, in fact many graphs, which can indeed be determined by just looking at the eigenvalues. Okay, so you are given with the eigenvalues, you are 100% sure that the graph will be only this. There cannot be any other graph with different structure, basically non-isomorphic, which have the same eigenvalues. Okay, so and we will be taking very simple examples, but even though there will be few cases where this proving that there cannot be any other graphs with the same eigenvalues, this thing is slightly tricky. We will see that, and we will make use of sometime Cauchy-Interlaced theorem and sometime many other graph properties. Okay, which are related with the eigenvalues. Okay, so let us start with a very simple case of complete graph. Okay, so complete graphs are determined by the eigenvalues. So let me write this statement and then we will prove that. Very interesting one. Okay, the complete graph let me write it, Kn on n vertices, okay, is determined by the eigenvalues of the adjacency matrix. Okay, of the adjacency matrix. Very good. And we will also tell, in short form we will say that ds determined by the spectrum. Okay, so by the eigenvalues. Okay, let us go to the proof. Very simple one. So what are the eigenvalues? So eigenvalues of Kn are what? Eigenvalues of Kn are what? We have already seen it many times. So n minus 1 and then minus 1 dot minus 1, and I think these were the multiplicity with n minus 1. Okay, we have to prove that with this spectrum there cannot be any other graph except the complete graph on Kn. Okay, so suppose okay, and in fact actually without contradiction also we can see. Okay, so let us see, suppose H is a graph with this same spectrum, right, with eigenvalues, okay, this n minus 1, okay, and up to n minus 1 with multiplicity this. Okay, one thing is for sure, in H how many vertices will be there? There will be n vertices because there are n eigenvalues. Okay, so n vertices. So what we can deduce here? So there are n vertices in S. Okay, how many edges are there? Okay, very good. So can we determine the edges, number of edges, just by looking at the eigenvalues? Indeed, right? So we know that summation over degrees, sum of all the degrees divided by 2 indeed gives us the number of eigenvalues. Okay, so sum of degrees is nothing but twice the number of edges, right? Twice the number of edges, we know that. What are the degrees here? Okay, so degree here, if you see that, what is the sum of degree. How can we write sum of degree in terms of eigenvalues? Okay, so this we have already seen. Okay, what we will do, we will square the eigenvalues and then take sum of it, right? This is nothing but sum of squares. So squares are what? N minus 1 plus the squares of minus 1, but how many minus 1 there? There are n minus 1 squares, right? So n minus 1 times this number. Okay, which is what? So this is nothing but n minus 1. I can take n minus 1 common here, and this is nothing but n, right? Okay, and this is what? Twice the number of edges. That implies that number of edges are nothing but n minus 1 times n divided by 2. Okay, what it tells? This tells that every vertex is actually have connection with every other vertex, otherwise this n into n minus 1 thing will not come into picture, right? So basically every vertex is connected to have an edge with every other vertex. That means the graph is complete. Okay, so this implies that H is a KN. Very simple one. Okay, very good. And by the way, there can be any other proof also. There can be another proof also. So if you see that, I will give you just one hint. If you talk about Kn, okay, if you talk about Kn, and suppose n is greater or equal to 3, for k equal to 1 to this, the argument that I am going is very trivial. Okay, if you just see the structure of complete graph. Okay, we see that there cannot be induced P2. So there is a path on suppose 3 vertices, or maybe the 2 edges, just 1, 2, 3. So this is P2. In any complete graph on vertices which are more than equal to or more than 3, okay, there cannot be P2, because the one will be having, suppose this is an induced P2, then this will be a contradiction, because 1 and 3 will have an edge, right? So there cannot be any induced P2 on a complete graph on vertices at least 3, right? And then we can actually, but just looking at the eigenvalues, we can indeed tell that if these are the eigenvalues, there cannot be induced P2. Why it is so? So this is maybe I will call second proof. Okay, second proof. Okay. Now suppose if there is an induced P2, what are the eigenvalues of P2? The eigenvalues of P2 are this, right? The square root of 2, 0, because this is a bipartite graph, and in fact this is a star graph on K1, 2, right? So this is nothing but this. Okay. Now, and what are the eigenvalues of given to us? The eigenvalues given are what? N minus 1, and then the rest of the eigenvalues are 1, 1, minus 1. Okay. Now with we know by interlacing theorem, Cauchy interlacing theorem, okay, suppose this is lambda 2. So lambda 2 is always greater or equal to the lambda 2 of the eigenvalues of the lambda 2 of P2. But lambda 2 is here minus 1. Okay, this should be ideally this, right? If if there is an induced P2, but this is a contradiction, right? So this is a contradiction. Okay, hence there cannot be any P2. Okay, hence there cannot be any P2. This implies that the graph has to be complete graph when n is greater or equal to 3. For n equal to 1 and 2, results are just by looking at the eigenvalues. You can just at one case there will be just 1 point, in another case there will be just 1 edge on 2 vertices. Okay, very good. So this is another proof. Okay, now let us move to another graph. Okay, and this graph is Bell complete bipartite graph. Okay, another graph is complete. Okay, theorem. Okay, this one. Okay, we will see that as we will go ahead. Okay, things will get slightly trickier and trickier. Okay, so complete graph, bipartite graph, balanced bipartite graph, KNN is DS, determined by the spectrum of the adjacency matrix. How can we prove that? Okay, the eigenvalues of KNN are what? Proof. Okay, the eigenvalues of KNN are, what are the eigenvalues? Okay, square root of m, and so basically the eigenvalues will be here, right? So this is nothing but n, then minus n. Okay, because it's a bipartite graph. Okay, eigenvalue so will be this. So basically balanced bipartite will be like something like this, right? Equal number of vertices both sides, and everything is connected to every vertex from one part is connected to every vertex of other part. Okay, very good. So yeah, like this one. Okay, and other eigenvalues will be what? This will be zeros. okay, and these will be how many times? So there will be 2n minus 2, okay, because there are 2n vertices. Very good. So let G be, or I mean H be, let H be a graph with the same eigenvalues, okay, with eigenvalues this, right? So let me again write n dot 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 0, then minus 1, and this is coming 2n minus 2 times. Okay, now what we can deduce from here? Let us check out what the edges we can find. Yes, definitely, but by just knowing the edges will come out to be n square, right? But just by looking at these edges can be determined whether this is no. There can be many other graphs with n square edges, right? And then vertices we know. Okay, so there are 2n vertices here. Okay, very good. Okay, here we need a slight trick, that more trick than what we use for complete graphs. Okay, so maybe we can find the average degree of it. Okay, so let us calculate the average degree. Okay, average degree. Okay, now average degree is what? You sum all the degrees and then divided by n, right? So what are degrees here? So degrees, and then, but can you determine degrees by the eigenvalues? Yes, we have just seen that. So average degree is nothing but if it is sum of degrees divided by the total number of vertices, right? But sum of degree is what? Sum of degree is twice the number of edges, which is indeed given by, just we have seen that, right? We have just made use of this. You square the eigenvalues, okay, this will give you twice the number of edges, and then you divide it by n. Okay, square the eigenvalues. Okay, so 0 square, and this is actually 2n minus, it doesn't matter. Okay, so let me actually multiply this, 2n minus 2, 0 square, plus again this is square. So this will give you what? This is square, so sum of a square of this is giving you sum of degrees, right? So sum of degrees, okay, sum of degrees, okay, and then you divide it by n, right? You divided by the n number of vertices, right? So suppose sorry, there are 2n vertices here. Okay, so 2n. So this is indeed giving you what? Oh, this is giving you n. So basically average degree is equal to n. Very good. But we have seen in the exercise, in the tutorial, we have maybe 3-4 lecture back, right? If the largest eigenvalue is equal to the average degree, if the largest eigenvalue is equal to the average degree, then the graph has to be regular. Okay, now since the largest eigenvalue eigenvalue equals the average degree, H is an regular graph. Very good. So basically every vertex has the same degree. And in fact, just by looking at the number of edges, and we can indeed find the number of the degree is indeed n, and that degree is which is n, right? And the graph is bipartite. And every vertex has the same degree, and the number of edges is again what? And number of edges is what? You just do the same calculation, it will come out to be n square is n square. Okay, that means this implies further that graph has to be, the H has to be KNN. Okay, very simple one. Okay, a slightly tricky one. We have actually made use that if the largest eigenvalue is equal to the average degree, then the graph has to be regular. Okay, very good. Now let us move to another example, which is again very simple one. Again very simple. The same technique we will be doing here, and this is for cycle graph. Okay, and by the way, just think about what will happen for other graphs. So this is a DIY, other complete bipartite graph. What about KMN? What about KMN? Okay, what about KMN? Okay, just think about this, right? When n equal to 1, we have proven that it is determined by the eigenvalues. Okay, let us see another example. Okay, so cycle graph. Okay, cycle graph Cn is ds. It's again very simple. So what are the eigenvalues of Cn? The eigenvalues of Cn are, so this is by the exercise we have seen this question in exercise 2, right? The eigenvalues of Cn are what? It's actually 2 cos 2 pi k divided by n, where k moves from 0, 1 to up to n minus 1. Okay, and now how can we say that a graph with these eigenvalues has to be a cycle graph? Okay, just immediate two things that we can deduce from the eigenvalues: the number of vertices, which is m, number of edges. Also, we will just make use of eigenvalues. We can actually figure out that number of edges are also m. So this has to be what? Same number of vertices, same number of edges. So this could be a collection of cycles, right? But we have to prove that this is just one cycle. In fact, if you see that the largest, and another thing is what? The argument same. So let me write down the hint, or whatever hint. Find the average degree. Find the average degree. Okay. This will be equal to, this is equal to 2 actually. This is equals to 2. Okay, that means this again is regular graph. We will just do the same proof as we have done for k and n. Okay, so this implies so that implies the graph, or maybe I could have called edge h. The graph is regular. In fact, regular with degree 2. Okay, 2 of each vertex. Okay, degree 2. So maybe I can write it just like 2 regular, right? So maybe I can write it's a 2 regular graph. Okay, and rest of the things I will erase it. Okay, so now is it enough just by looking at this that it is only basically just 2 regular graph? Is it enough to say that this is cycle graph? No, there can be more component, right? What thing will which argument we will make to actually prove that this is indeed a cycle graph? It's not a collection of cycle graphs. Okay, what is that argument? The argument is the multiplicity of the largest eigenvalue. Okay, the multiplicity of the largest eigenvalue. The largest eigenvalue here is what? It is 2. Okay, which are the multiplicity is just 1, which is the eigenvalue is 2 with just multiplicity 1. Okay, so there cannot be more than one component, right? There cannot be more than one component because this is a regular graph. Okay, and so there will be only one eigenvalues which will have value 2. Okay, so this will tell that the graph is indeed. So this implies, in fact, let me write. Okay, the multiplicity of 2 is 1. Okay, eigenvalue is 2 is 1. So this implies that the graph is Cn. Very good. Okay, so now let us go to a very interesting example. And at the first glance it looks like, oh, it's very simple. It must be very easy to tell whether this graph is determined by the eigenvalues or not. Okay, so let us see this example. The example is of path graph. the path graph Pn is determined, or I mean is ds. Okay, so maybe now right, determined by the eigenvalues of the adjacency matrix. Okay, how can we prove that? Okay, let me first write down the eigenvalues of it. Okay, so the eigenvalues, so we have seen it again and again. So okay, so the eigenvalues of Pn are what? So these are 2 cos pi k, and it should be n plus 1. Okay, where k goes from 1 to okay n minus go to n, right? Here I think I have done it correct. Yeah, correct. Very good. Okay, very good. Okay, what will be the largest eigenvalue? The largest eigenvalue is strictly lesser than 1. By the way, there will be what? How many number of vertices? There will be n number of vertices, and you just by looking at basically the sum of degrees, and you do this, you will be getting the number of edges are indeed n minus 1. Okay, so number of vertices equal to n, number of edges equal to n minus 1 from spectrum. Okay, so now let H be a graph with eigenvalues. Let me actually again write eigenvalue is the same, right? 2 cos pi k n divided by n plus 1, and k varies from 1 to. Okay, so now with these eigenvalues, okay, what will be the largest eigenvalue? Okay, the largest eigenvalue is strictly lesser than 2, is less than 2, right? Due to this formula. Okay, so we have seen this formula many times. Okay, that means what? This implies what? This implies what? There cannot be any cycle. There cannot be any cycle inside G. Okay, in CYCLE, cycle in H. Sorry, H I am right. Yeah. Okay, very good. So there cannot be any cycle. Okay, very good. Similarly, if you see that, because cycle has the largest eigenvalue 2, right? And by interlacing theorem, this cannot. So cycle cannot be an induced graph. So basically, CK cannot be an induced subgraph. In fact, let me write it CP. Okay, so because K I have used. Okay, very good. So CP for any P cannot be any P be basically P greater or equal to 3 cannot be induced subgraph of H. Okay, by interlacing theorem. Okay, so this implies that again next thing is H is a tree. There are n vertices, n minus 1 edges, and there is no cycle. Okay, H is a tree. Okay, now what you see that if you talk about this subgraph, right? This can also not be induced subgraph. Basically, this is what K1 4. The eigenvalue of K1 4 are what? These are 2, 0, 0, minus 2. In fact, one more 0 will be coming out, right? So this cannot be the induced subgraph of H. Why? Because the eigenvalue, the largest eigenvalue of here is again 2, right? Again by interlacing theorem. Again. So let me write again by interlacing theorem. lacing theorem or interlace theorem, K14 cannot be an induced subgraph, subgraph. Very good. Okay, cannot be induced, otherwise this will violate, right? Because this eigenvalues must be less or equal to the eigenvalues of the largest eigenvalue of graph, but the largest eigenvalue is always less than 2 here. Okay, very good. So very good. Now next thing is, that means there cannot be any vertex with the degree 4. This implies there cannot be any vertex in H having degree 4. Okay, degree equal to 4. Okay, now next what? So there can be vertices of degree 2 or degree 3, right? But if there are vertex of degree 3, then this is not a path, right? This is not a path graph, right? Okay, so we have to actually prove that, there cannot be a vertex of degree 3. Okay, let us first see this, a very, very tricky part here. Just check this structure. Okay, suppose inside the graph there is this structure, such kind of structure. Okay, and of course there can be other things, right? And this will be this will be this. Okay, okay, so okay, our claim is such structure cannot be there inside H. If this is a substructure or induced subgraph, then again the largest eigenvalue of this will be 2, and this will give a contradiction using Cauchy interlace theorem, because the largest eigenvalue of our H is strictly less than 2, but the largest eigenvalue here will be 2. Indeed, if you see, let me draw this structure separately. Suppose if this is the structure, okay, for some this, okay, so suppose there are some k vertices here, right? You can cook one eigenvector. You can cook one eigenvector indeed. So what you do, wherever the degrees of the vertices are 1, okay, so you just put 1s here, okay, and rest of the place you put 2, 2, 2 and 2. Okay, so basically here, suppose if I number them 1, 2, 3, 4 here, so this will be 1, 1, 1, 1, and rest of the place you put 0. This will be an eigenvector, okay, so of this graph. So this is an eigenvector, okay, and the corresponding eigenvalues too, and the corresponding eigenvalue is 2. This is actually very easy to see. If you see that, so all vertices of having degree are incident on a vertex of degree 2, which we are giving the weight 2, okay, and then every vertex which we are giving value 2, okay, these are having edges with either basically the adjacent vertices are both the adjacent vertices are having either 2 and 2, or there is one adjacent vertex having 2 and rest of the 2 vertices have 1, 1. So in total the sum will be for them the sum will be 4, for them the sum will be 2. Okay, so this is just a simple matrix multiplication. You just draw the adjacency matrix of this and just play with this graph. It will be equal to 2 times the same vector. Okay, very good. So this is an eigenvector corresponding to this subgraph, okay, and the corresponding eigenvalue is 2. So basically this cannot be induced subgraph of H, because then there will be a contradiction using Cauchy interlace theorem. Okay, so now what? So there cannot be basically 2 vertices having the degree 3. Okay, there cannot be two vertex having degree. So this implies there cannot be vertices having degree 3. Okay, degree 3. So there can be at most one vertex having degree 3. So let us see that case. Okay, now see the case. So maybe now the structure could be this, right? Structure could be this. So dot dot dot. Okay, and let me make one more, and there will be some vertex here. Again there will be some edges. Okay, here, and then there is rest of the. Okay, so there is suppose one vertex which is having this, let me call it U, and this is suppose V. Okay, and let me call some other name, maybe A and B. Okay. Okay, very good. Now how to prove that this is also not possible? How to prove that this is also not possible? Okay. Okay. Now remember, I gave you an exercise maybe in maybe 6th or 7th lecture, I don't actually recall. Okay, the exercise was this. Okay, suppose if you move one branch, if you pick suppose this, so there are two branches here, right? So one branch is suppose this one, another one this, and you just treat this as a path. Okay, now suppose you move one out of these two branches, okay, to one end of this, right? So basically, so let me write it down here. So suppose if I do this, the same thing, right? And I move this part, so to here. So this is my V, this is U. Now this dot dot dot, and then there will be an edge, and this vertex A. Okay, and now the same thing here. So this is this, right? Dot dot dot. Okay, B. Okay, now if you see that the number of now just check the number of closed walks of length 4. So let me call it A, or just B. Maybe I can call it this S and T, right? So these are two. Okay, there will be a difference. The difference will be of 4. The difference will be of 4. We have seen this in our exercise. Okay, I actually do not remember. So again, you just check it. So this is a DIY for you, just to check that. Okay, the number of the closed walk of length 4 here will be differing. For if this is the case, then the number of closed walk will be differing here. And now the number of closed walk of length 4 are given by the eigenvalues, right? But here the same eigenvalues are giving the different, right? So which is a contradiction. Hence this structure also cannot be there. Hence, okay, hence by the eigenvalues, using the eigenvalues argument, or just by looking at the eigenvalues to the power 4, okay, we conclude that this structure, basically S is also not possible. S is also not possible. That means possible. So there cannot be any vertex. There cannot be any vertex of degree 3, and that means the graph is, this implies that H is Pn. Very good. So thank you very much. Okay, I hope you enjoyed this lecture. If not clear, you just revise it again. Very simple one. Okay, and thank you very much, and see you in the next lecture.